Hey guys, I think the recording started, so I'm gonna share my screen. All right, you should be able to see our practice problem now. So we've got a girl here curling some dumbbells. So the question is, the girl is curling 25-pound dumbbells. What is the elbow flexion torque caused on the arm in both beginning and end positions? And then what is the force in the bicep in each position? So if you notice, this is really similar to the question we had in on the homework, the fifth one that I've been explaining a lot. This one's a little bit more simple though, because we don't have to worry about body position changing. Because in that one, the body position, like his hips or the guy's hips went forward, so the moment arm of the glute max changed, and also we had to worry about the head, arms, and torso. This one we're standing upright and just the elbows are moving, so we don't have to worry about all that stuff. I just wanted to have a little bit. We don't have any simple examples, so this one's a little bit more simple. Another thing that I want to point out that's also in the practice problems that he sent out, on the one with the push-up, when it's talking about the tricep, try not to think of that as a tricep force. Try to think of it as an arm extension force, and that might help you with your force vector that you need to draw. Because on the one from the homework, it was a hip extension torque for the glute max, not necessarily like the glute max torques. So think about like how the body is moving, not necessarily the line of motion of the muscle. So like with my tricep, if I were to extend it, we would agree that like the muscles run this direction. So it'd be running downwards, but the arm is moving this way. So like my force vector for that would be that way, right? This is my axis of rotation right here, my elbow. And the thing that's moving is my arm. It's an elbow extension force. So like from this position, it would be moving this way. From this position, it would be moving that way, right? Just the direction of extension, and that'll help you get the rotation around the axis. So don't think of it as the actual muscle. So for here, I worded it as elbow flexion torque to make it a little bit easier. So the first thing that we need to do is determine the direction of rotation of our torques after we figure out what torques that we have. So in this one, we've only got two torques. We have the torque of the dumbbell and the torque of the bicep flexion force. So here's some free body diagrams right here. You can see that they're labeled beginning and end. So on the left, we have our initial position. So as you can see, the dumbbell is down beside her waist. So we have the force of the bicep flexions, the arms move upwards, right? And it doesn't have to be perfect. That line could be, I don't know if y'all can see my mouse, but it could be a little bit more diagonal. It's still going to be the same direction around the axis of rotation. It's still going to spin the same way. And then we have the dumbbell. It weighs 25 pounds because of gravity, right? I didn't give you a mass, I gave you a weight. So you don't need to convert from gravity. You just need to convert to newtons. So there's those two. And then in the end position, the arm is a little bit more up. And make sure you're checking your rotation around the axis for both positions if this is a thing, because in your sum of all torques, the signs could be different. Like if for whatever reason one crossed like the axis of rotation, it could potentially be facing the opposite direction. So always go back and check your force applications around axis of rotation. In this case, it still happened to just be the same, but just to make sure that you're looking at everything. So same thing, biceps torque is still up, you know, coming from the center of mass of the thing that's moving. And then for the dumbbell, it's still gravity's gravity, it's downwards. So we have forces moving in opposite directions. Our axis of rotation for this guy is the elbow joint because bicep. So I drew a little tiny dot on the elbow joint for that. So we're moving for the bicep force in both cases, we're moving counterclockwise. And for the gravitational force, we're moving clockwise. So we know counterclockwise forces are positive and clockwise forces are negative. So that means our bicep torque is going to be positive and our dumbbell force is going to be negative. I just wrote that as GT for gravitational torque instead of, you could write DT, whatever you want your variables to be, just make sure you stay organized. Another thing that I went ahead and wrote out on here is I gave you all a table similar to the homework. So I gave you the moment arms in this table, and I just left them in centimeters just to make you think about changing the meters, but so you don't have to do the inches to centimeters bull crap. So the moment arm of the dumbbell in the very first, the beginning part is just 5 centimeters. So you can see that down here. 5 centimeters away from our axis of rotation. And then the other one is 30. So as you curl a weight, right, your arm is getting farther from the joint. This is the farthest it ever gets from the joint, right? And now it starts to get closer, right? So the farthest away the hand is from the body where the dumbbell is going to be, this is where the most torque you would need to generate is. And then in my end position, in my beginning position, it would be the least. And if you think about that in real life, that makes sense, right? Because if the easiest part of a dumbbell curl is the first part, right? When you get really fatigued, you can do partials all day, right? You can swing that weight a little bit. It's getting to here is where it hurts, or it's the hardest, right? And also, if we're doing an isometric hold, that would be the hardest place to hold, right? If you thought about, it'd be really easy to hold the dumbbell up here or just down here, because you have to supply less torque or less force in the dumbbell. Holding it like this is going to be the hardest, right? So logically, our torque in the ends position should be a higher number. So if we don't get a higher number for torque, we probably did something wrong. So let's head over to our equations. So we figured out our torques, which we have 2 of them, and then we figured out their signs or which way they rotate. Those should be your first 2 steps. Identify torques and identify which way they rotate. So for the beginning, sum of all torques equation, we start with our ET, whatever, equals. We know our bicep torque is positive, so I wrote it as positive. And then we know our dumbbell or gravitational torque is negative. So bicep torque minus gravity torque. I like to get everything positive because the algebra is a lot easier. So I just added GT over to the other side. Remember that sum of all torques equals 0. So that's not a variable you need to worry about. Just throw it away. In reality, you could just write 0 equals BT, whatever. He would know what you're talking about. Now we need to solve. So what are we solving for? Bicep torque. So this guy right here, the bicep torque, I don't need to split that up into force and distance for the torque equation because I'm solving for it. Dumbbell torque, I do need to change, right? I need to change that into a force and a distance component, which is what you can see reflected here. And all of that is equal to bicep torque because that's what we're looking for. So I went ahead and converted my 25-pound dumbbell times my multiplier, whatever you get, 4.45. And I got my answer in newtons. Remember, this is kind of an odd question. And ask what's the elbow torque caused in the arm in both beginning and end positions. These 2 dumbbells are not connected, right? If this was a flat bar with 25 pounds on each side, then absolutely you would add them together. You have 2 separate dumbbells doing 2 separate things. So you can assume that he is just asking for one. If he asked for the total thing, then you would absolutely need to put it together. So you just need to kind of logic your way through that. Like I said, if it's a straight bar and it said it's a 25-pound straight bar with a 25-pound weight on either side, you would need to do 25 plus 25 plus 25 to get 75. We're only looking at one at a time here. So that's the reasoning behind 25 and not using the number 50. If I asked you what the total torque is between both biceps, then absolutely you need to do 50. Because the reasoning behind that is, remember in the glute max problem, we had to divide by 2 to find each. That's because they were working synonymously to move one singular kettlebell fixed between both arms. This is 2 dumbbells and these are 2 separate systems, okay? If he was to ask a question like this, he would probably just give you a perfect side view. This is the best picture I could find with both positions. He would probably give you a side view of just one arm curling. All right. I hope that makes sense. So I converted my 25 pounds to newtons. So I have 111.25 newtons. And then I gave you the moment arm over here of the dumbbell, which is 5 centimeters, which is 0.05 meters. Everybody knows how to multiply. You get your bicep torque is 5.56 Newton meters. Okay. Moving down to the end position. We looked at our free body diagrams already and determined that our signs don't change and our axes of rotation all stay the same. So I can use the exact same equation, which is exactly what I did. So same equation from the beginning position. Let's see if I can get that. There, now you can see both. Same equation. Did the same thing, added gravitational torque over, and I split it up. So we have the same thing going on here. The force of my dumbbell did not change. So it's 111.25 newtons still. What did change is my moment arm, which we have at 30 centimeters, which is 0.30 meters. Once again, everybody has a calculator and can multiply. That bicep torque is 33.375 Newton meters. And let's think about that logically. The farther away the hand holding the dumbbell is from the elbow, the more torque or force you need to apply in order to hold it up, right? It just logically, and we have that. The end position, the hand is farther away from the elbow joint, so we got a bigger number. So we're on the right track here. The second part of this question asks, what is the force on the bicep in each position? What equation do we know that involves force that is not dealing with acceleration? It's the torque equation, right? Torque equals force times distance, which we've used down here, and you guys are all very familiar with that by now, I hope. So we have a bicep torque, and I've given you a distance, right? I've given you 1 centimeter in each position, and I will explain why that one didn't change, and in the glute max problem, it did change. Bicep torque equals bicep force times bicep distance. I have a torque, I have a distance, and I need a force. Lucky for us, all three of those variables are included in the torque equation. So I plug my torque in here. My force is the unknown, so I leave it. And then my distance is 1 centimeter, so it's 0.01 meters. I do very simple division. I move my 0.01 meters over to isolate my variable on one side, and I do 5.56 Newton meters divided by 0.01 meters, and I get an answer of 556 Newtons. Okay. Let me explain to you why now in the end position, this is the same number. In the glute max problem, the hips moved forwards, right? So remember, the beginning position was a bigger distance away from the axis of rotation than the end position. If you go back and look at that problem, the reasoning is because when you are hinged over, center of mass was here, right? My butt is, or my glute max, to be medically correct, is farther away from my center of mass than when I extend my hips. So that moment arm changed. When I do a bicep curl, my bicep is not moving, right? My bicep is 1 centimeter away from the axis of rotation the whole time, unless I do some crazy funky stuff. And actually, even then, it still stays the same. I can do this, and my bicep's in the same place, right? My bicep would need to physically move away from my axis of rotation or towards it, and that's physically impossible considering the bicep is literally fixed to the axis of rotation, or technically in front of it, right? Because if it was fixed to it, we wouldn't be able to calculate torque. So going to the end position, we do the exact same thing. We over here, bicep torque equals bicep force times bicep distance. Everything on the right side of my equation stays the same. My bicep force, and we just said that the moment arm was the same. I just need to plug in my torque from the end position. That's how we get a different number. Bicep force equals 3,375.5, which once again makes sense because in this position, we would need to provide more force than in the other position to keep, if we were doing like an isometric hold, to keep the dumbbell up. You just have to provide more force in that position, right? I think that's all I need to explain. I'll say that out loud anyway. If you have any questions, just let me know. I will not be on campus tomorrow, but I'll probably be doing biomechanics during the Friday review session in anatomy. So yeah, if y'all got questions, let me know.